actually become a little bit more important when I show you about this one I just like had you pick up today, the percent composition thing. The percent composition, because you're going to be dividing values by each other, your calculator can show you all kinds of different numbers of digits. It's important to express the percents with an appropriate number of significant figures. So anyway, that's what you get. I'll get for like that. That's calcium carbonate. That's a limestone. That's the mineral that coral builds to make its structure in our fish tanks. So then there's potassium carbonate. So you got two potassiums, two carbons, one carbon, and then three oxygens. Well, the only thing that's different here is the potassiums. So potassium's like 39.10. So that comes out to be, let's see, well, 78.02. And the carbons and oxygens, they're the same as what we just had. So the only real difference is the potassium mass is different. This is a common thing that you end up doing some math for when it comes to like single replacement reactions. So in a single replacement reaction, it could be like potassium replaces calcium, and the carbonate, the CO3, the components of that stay the same. The 12.01 and the 48, they don't change. The only thing that's changing about the compound is that like you're replacing a potassium with a calcium, replacing calcium with potassium. You got to compare the position on the activity series, and as a result of that, you end up with a total different mass. Let's see, 130 K2, 39.1 times 2. Oh, 78.20, not 02. There we go. 78.2 and 12.01 and 48. Yeah, somewhere around 138.21, somewhere around there. So, I mean, that's kind of all you got to do. You got to, dig around on the periodic table and find them. Some of the masses you just get to know and memorize as time goes on. You don't have to memorize masses, of course, but have your periodic table handy. An important thing to notice is that when the compound exists, the different parts of the compound weigh a different amount. So, although there's one calcium and one carbon in number 3, the mass of calcium is more than 3 times greater than the mass of the carbon. So when it comes to the mass of the compound, the different components have a different mass. That's the thing I want to show you about how to calculate that today too. All right, we did number 5. Came out to be like 278.18, somewhere like that. Number 6, H2SO4. That's sulfuric acid when it's in solution. So we've got there's 2 hydrogens, 1 sulfur, and 4 oxygens. Hydrogen's got a mass of like 1.01. Sulfur is like 32.07. Oxygen is like 16.0. So what's that going to be? 64. That came out to be like 98.09. I'll write the calcium hydroxide up here. So we got a calcium, and there are 3 oxygens because this hydroxide, OH, is inside a parenthesis. There's 3 oxygens and 3 hydrogens. So I got 3 oxygens, 3 hydrogens. I just wrote O twice. So calcium's 40.08. Oxygen is 16.0. and hydrogen's like 1.01. .08. So that's like 91.11. And this U, you know, that this unit for now, that U stands for like the unified mass unit. And it turns out that the standard for that, you'll notice that the mass number is pretty close to the you know, the number of protons and electrons. We kind of already figured out those unified mass units. Those are the average atomic masses of all the different naturally occurring isotopes. Because whenever we, you know, find and work with like carbon, although the mass of carbon-12 is exactly 12, it's 12.01 because there's also carbon-14 that's common on the Earth. Oh, this should say Ca, not C, calcium. But the rest is right. Then there's this aluminum carbonate. So I got 2 aluminums, 3 carbons, and then 9 oxygens. Because whatever's inside the parenthesis or outside the parenthesis gets multiplied by whatever's inside the parenthesis. So let's see. Aluminum's 26.98. Carbon's 12.01. Oxygen 16. And 44. So like 233.99, something like that. Okay, now number 9 is a special case, thing that you need to know how to do. We studied hydrates. Hydrates are compounds where there's water molecules for every ionic compound. And the thing about hydrates is you've got to include the mass of the water with the mass of whatever compound is with the water. So number 9 is copper sulfate pentahydrate. If you remember how to name those. So this, you can call it, I'll write it out. It's this is copper 2 sulfate pentahydrate. So I know it's copper 2 because the sulfate anion has a charge of 2 minus, and in order for there to be 1 copper for every 1 sulfate, it's got to be copper 2 with the sulfate. And then 5 is penta, and 5 water molecules for every copper 2 sulfate pentahydrate. So here's the thing you got to do. For every 1 copper sulfate, there are 5 waters. So we've got a bunch of different elements going on. I'll write it here. There's a copper, there's sulfur, and I'm going to actually write the oxygens separately just so you can see the way that this goes kind of like conceptually. There's 1 copper, 1 sulfur, 4 oxygens. And then there are 5 water molecules. So the 5 out front, much like, you know, if it's like an algebraic equation, maybe I have like 5 times, you know, 2x plus y, you distribute the 5 in. So that's the same as having like 10x plus 5y. In other words, you multiply the coefficient out front by anything that's inside. Here I've got 5 waters, so it's 5 water molecules, and every water molecule has 2 hydrogens. So 5 times 2 must be 10 hydrogens. And then there's 5 times 1, or like 5 more oxygens. But, instead of writing the list of all the elements out, having oxygen here and here, which is kind of dumb, you just have a total of 9 oxygens. So instead of like having oxygen twice, I'm just going to write, make this 9. Really, it's 4 from the copper sulfate, and then 5 from the 5H2O. So you got this compound has 1 copper, 1 sulfur, total of 9 oxygens, and then 10 hydrogens. That's the way you deal with the hydrates. Let's see, 63.55. Sulfur is 32.07. Oxygen 16.0. Hydrogen is 1.01. Get rid of that little thing there. 249.72. Well, that's weird. That little circle thing. That's like the eraser part of it, but it's not even on this screen. Let's see if I can. That's weird. It's different here than it was there. All right, NH420. So there's a 2 outside of the parenthesis. I got 2 nitrogens. There's going to be 8 hydrogens, and then just 1 oxygen. So it's critical to be able to get the numbers of atoms correct. Let's see, 28.02 and 8.08 and 16. 52.10. So that's it. That's the procedure. You make a list of all the elements in the compound, write how many of each atom exists in the compound, multiply it by the formula mass on the periodic table. They get you the total mass for each of the elements, and then you add them up, and it tells you the total mass of the whole compound. It's fairly simple. That's the basic thing you got to be able to do. Okay, let me share this real quick. Okay, so if you're remote in the, there's a new folder. Well, for everybody, there's a new folder that says Unit 7, and it says Stoichiometry. This is a great word. So the prefix or the suffix metry refers to measure. This word stoichiometry here, let me just write this. So the word stoichiometry, metry means to measure. It's just like any other metry, like geometry means to measure the earth. Geo is earth, metry means to measure. Or, I don't know, trigonometry, that's to measure triangles. Stoichiometry, so we're going to measure some stoichios. Stoichio is not a common prefix that you're familiar with, but this stoichio refers to like quantities of chemicals. So really what we're talking about is measuring quantities of chemicals that take place or take part in chemical reactions. That's what stoichiometry means. So in the beginning of the course, it says like, or in the top of the course folder, it has Unit 7, Stoichiometry. Inside that folder, there's a folder from last week. It says week of 12/15 to 12/19. But we just started the unit at the end of the week. The Intro to Formula Mass notes and the Formula Mass assignment, the thing we just went over, that's inside that folder. The one for this week, week of 226 or 222 to 226, that's this week. There's a schedule for the week. Like we just went over those formula mass problems. I want to go over very briefly about the rules for significant figures and then show you about how to do percent composition. But I'm going to do it practically. So there is a set of notes in here. It says percent composition notes. This is like if you're absent or you need to refer to this. The percent composition notes has 2 pages about the rules for significant figures or significant digits. And we already talked about significant digits earlier on in the course, but I'm going to show you practically how it applies to dealing with percent composition. Basically, when you add or subtract, you round your answer to whichever of the values has the fewest number of decimal places. When you multiply and divide, your answer has as many significant figures as whichever value has the fewest number of significant figures. Like 6.99 has 3 significant figures, and 0.25 has 2 significant figures. So although your answer might have a whole bunch of significant figures, you round the answer to only 2 because the 0.25 only has 2 significant figures. There's a thing in here about percent composition, and you can read through this and it has some steps, but I'm going to do it as practical examples so that you can see like what the plan is. And this is the biggest thing you've got to be able to do. So the thing that you picked up when you came in, or if you're remote, there's this thing that says percent composition in the thing for this week, in the folder for this week. And it has examples of calculating percent composition for different compounds. If this thing will ever open. There we go. So there's an example at the top about percent of oxygen and iron hydroxide, iron 3 hydroxide. But these 2 examples of water and sodium sulfate are very useful and very good examples. So let me show you what I mean by what percent composition is and how you do the math and stuff. Let me find that first page. I think it's up here. Here we go. Okay. Let me get rid of that. And I got to get this thing, drag this up. All right. Water. The molecule water. There's 2 hydrogens and there's 1 oxygen. So to most people, when you look at this compound, you're like, well, there's twice as much hydrogen as there is oxygen. And in terms of the number of atoms, that's true. For every 1 oxygen, there are 2 hydrogens. So one way you can, illustrate it is I could say, well, here's the oxygen, and then there's 2 hydrogens, and those 2 hydrogens are bonded to that oxygen. And it's true that there are twice as many hydrogens as oxygen. But when you calculate the formula mass, so the first step here is to figure out the formula mass for water. If I take and write the things that exist in the compound, there's 2 hydrogens and 1 oxygen. Hydrogen has a mass of 1.01. So the 2 of those together are 2.02 U. The oxygen, 16.00. And that comes out to be a total of 18.02 U. Each oxygen atom weighs like 16 times more than any hydrogen atom. And despite the fact that there are twice as many hydrogens as oxygen, if you look at the masses of the different elements that go to make the total mass, the vast majority of the mass of this compound is the oxygen molecule, is the oxygen atom. 16 out of the 18U is from the one oxygen. So despite the fact that hydrogen, there's twice as many of them, they're so low in mass, they don't contribute much mass to the compound. So it is important to consider that H2O is twice as many hydrogens as oxygens, but as a percent of the mass, most of the mass of the molecule is the oxygen. So here's what you do to calculate the percent composition, because this problem says calculate the percent hydrogen and percent oxygen by mass, not by numbers, but by mass. You just take the mass of the total number of atoms in the compound for each element and divide it by the total. So here's what you do for the percent hydrogen. The percent hydrogen is equal to 2.02U divided by 18.02U. All you got to do is take the mass of hydrogens, there's two of them, and divide it by the total mass. Now, when you do this on your calculator, you can get all kinds of different numbers of digits. My calculator has 0.1120976693. It just keeps going on forever after that. So that's an inappropriate answer for two reasons. It's expressed as a decimal, not as a percent. So we want to express it as a percent. And you know that to express a decimal as a percent, you just move the decimal place over to two places, because percent means per hundred. But the other thing you need to do is determine how many significant figures there should be in this answer. And how you do that is you look at how many significant figures or how many significant digits are in each of these two values. The numerator has 3 digits and the denominator has 4 digits. So this answer should have 3 digits. So instead of 0.1120976693, that is 11.2%. You've got, it's expressed as a percent, and you have an appropriate number of significant figures, 3 significant figures. Now the percent that's oxygen, you might say, well, can't I just like subtract 11% from 100%? And yes, you kind of can, but there's reasons why you don't want to do that. First off, when you take 16 divided by 18.02, this comes out to be 0.8879023307. That's what my calculator says. Each of these two values has 4 significant figures. So this can have 4 significant figures. The decimal place is going to go after the second 8, and I can have 4 significant figures, 88.79%. Now, you might say, well, 11.2 plus 88.79, that's only going to be 99.99%. And that's right. And that is okay. Sometimes proportions don't add up to be exactly 100. They could add up to be 101 or 99. That's a possibility. So let me show you, like, a for instance. If you take a pole and take a measurement that only has 3 significant figures, and let's say that one of the values is like 45.45%, and then the other value is 54.54%. But if you needed to round these to the nearest tenths place, this is 45.5%. That's not the example I wanted. I need to go down. Let's see. I got to think of a better thing. 5.1. Let's see. If I go 5.4. I don't know. I can't think of a good example real quick. But sometimes you'll see like a poll might be taken, and it might be like 90% have one preference, and 7% have another preference, and 2% have another preference. And you're like, well, those add up to be 99. They did it wrong. This could be 90 because it was like 89.5, and this is 7 because it's like 6.5. Let's see if those are right. 89.5 and 6.5. That's 96. That's too high. I don't know. I should have worked up a good example beforehand. Sometimes the numbers will work out where by rounding, you've had to round two of them up and round one of them down. Or if you have to round two of them down and one of them up, then they won't come out to be an exact sum. More importantly, if you calculate each of the percents separately, you can add them up to see if it comes out to be very close to 100%. They should come out to be very close to 100%. But nonetheless, each of these percents should be evaluated with an appropriate number of significant figures. So in this case, there's only 3 significant figures. In this case, there's 4 significant figures. That's an appropriate way to get the right thing. Okay, so that's the simple way to calculate a percent composition. All you got to do is the same thing we've been doing, just take and figure out the formula mass, but then the percent that's each element is the mass of that element divided by the total. In a water molecule, 88.8% of it by mass is that one oxygen. And then each of the hydrogens together is, 5.5, 5.6%, or together the 2 hydrogen atoms are only 11.2% of the total mass of the compound. So sometimes we care about the mass, and that comes out when we go to weigh the stuff out. And other times we care about the ratios. So there's a 2-to-1 ratio of the number of atoms in the compound. By number of atoms, this is 66% hydrogen, and then 34%. Well, this is actually a good example. 33% oxygen. Well, it'd be 67%. Like 67% hydrogen. So by number of atoms, it's 67% hydrogen, but by mass, it's only 11.2% hydrogen. By number, it's 33% oxygen, but by mass, it's 88.79%. Okay, another thing to know is it's true that if you were to multiply the percent by the total mass, then you get the mass of just the part that's in the compound. So for instance, in this next one says sodium sulfate, Na2SO4, it's 32.4% sodium by mass. I mean, how you figure that out is the same thing as we just did up here. So there's 2 sodiums, 1 sulfur, 4 oxygens, and those are multiplied by the masses of each of the things. So it's already worked out, but I want to show you like the way in which you know that kind of thing. This is 22.99. Oh, that got messed up. The sulfur, 32.07. 3264. So how much this compound is sodium by mass, just this isn't like part of the problem you have to do, but how the 32.4 is solved for is by taking 45.98 and dividing it by 142.05. The numerator's got 4 significant figures. The denominator has 5 significant figures. 45.98 divided by 142.05. Yeah. So it's 32.37. This would just be a problem as if it's only got 3 significant figures. But the whole point is this percent is not just the percent of each individual compound that's made of the sodium, but if you have a sample of sodium sulfate, so if this is a chunk of sodium sulfate, let me make my chunk bigger. It's not as if it's in sections or whatever, but some of it is sodium, like a third of it is sodium. This is like 32.4% sodium. There's some sulfur, and the sulfur is even a smaller proportion, like this. And then there's also some oxygen. But you see, oxygen makes up the largest chunk of the compound. It's not as if there's 3 sections in the chunk or whatever, because the atoms are all, mixed together. This is a ionic compound, so that it's a nice regular crystalline pattern. But if the total mass is 30 grams, the mass of it that is sodium, this problem is actually just taking the percent times the mass. But when you multiply a percent by something, it should be expressed as a decimal, like 0.324 times 30 grams. Let's see what that is. 0.324 times 30, 9.72. So in a chunk of sodium sulfate, if the chunk's total mass is 30 grams, and if it's 30.4% sodium, the mass of the chunk that is sodium is 9.72 grams. Always express percents as a percent, but whenever you do the math, you got to do it like with decimals. You don't do them as, you don't write or type in your calculator 32.4. Instead, 32.4% is 0.324. So I don't know. There's some other ones on here. We'll just do like one more of them, and then you can do the rest for practice. So number 3, what percent by mass of magnesium bromide is magnesium? Let's see. I got to get a new page. So magnesium bromide, MgBr2. First thing you do, make a list of the elements that exist in the compound and write how many of them are in the compound. 1 magnesium, 2 bromines. Magnesium has a mass of 24.31. Bromine has a mass of 79.90. So in this case, not only are there twice as many bromines as magnesium, but bromine also weighs so much more than magnesium does. So you can expect that the percent of this compound that's bromine is going to be mostly bromine. $79.9 by 2, 159. $184.11. So the percent that is magnesium is found by taking the total mass of magnesium, 24.31 U, and dividing it by the total mass of the compound, 184.11 U. So this on my calculator says 0.1320406.279. You don't want all that stuff. You only want 4 significant digits and expressed as a percent. So 13.20%. That means that the rest of it, like 87% of the mass of magnesium bromide is bromine. There are twice as many of them, and each bromine atom is, a little bit more than 3 times the mass of a magnesium. So because each bromine has 3 times the mass and there are twice as many of them, then bromine contributes about 6 times more of the total mass of the compound than magnesium does. That's all you'd have to do. If you also wanted to know the percent that's bromine, then you can calculate the percent that's bromine. Why this is useful is if you have a compound that's like an ore, like when we mine iron, you might mine like iron oxide or iron in some kind of a compound. And whenever you extract the iron metal, then you get a certain amount of iron, but then you get oxygen as well. The percent that's the stuff that you're looking for uh, in an ore is anything you mine from the ground to try to get a metal. The percent that is the metal you're looking for is called the assay. If you watch gold miners, like the gold miners show on like Discovery Channel on Friday nights and stuff, the assay of gold is really, really low. You see, they move a lot of dirt to get a really tiny amount of gold, but gold's also worth a lot of money. So they might, a whole dump truck full of dirt might give you just a couple little pieces of gold. Those couple pieces of gold might be worth, tens or hundreds of dollars, which is good. Gold's up like $2,000 an ounce right now, I think, which is good money. Let me see if I can find. So those gold miners, like on that gold mining show, the price of gold's about double what it typically is. $17.96. That's pretty good. Let me get new share. So this is the last 5 years for gold. So back in like 2016, the black number over there, $1,320 an ounce. It got to as low as $1,100 an ounce. And up here it did hit $2,000 an ounce. And it's 16 ounces in a pound. So that's $32,000 a pound for gold. It's a lot of money. So people also use it, not only is there value in the gold in the ground, but people use it as an investment tool. If you happen to have bought gold in August 2018 at $1,100, you could have sold it, this August for $2,000. But that 2,100 is a very, very high price. Is it like 1,700 an ounce? That's really high historically. 2012 it was at 1,700, but historically, like, I don't know. I used to work in a lab actually back in 2001 and 2003, and we used gold. We bought gold coins from the Canadian Mint because they're very high purity, and we were paying like, I guess, $340 an ounce. But now that same $340 is now $1,700. So the same research costs that much more money too.